Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3. Today we're gonna present our lab report, which is the Experiment 2, which is the flow measurement. Okay, first of all, for the abstract, the flow measuring equipment is intended to familiarize students with common method of incompressible fluid flow measurement, while also demonstrating application of Bernoulli equation. A sudden enlargement venturimeter, orifice plate, elbow, and rotameter are used to determine the flow. The manometers are used to determine the pressure drop associated with each meter. The purpose of the experiment was to find and compare the coefficient of discharge for a variety of flow measurement devices. This experiment was carried out with orifice plate and venturimeter, which are common for flow meters. The Bernoulli equation could be used to compute the volumetric flow rate of water using this flow meter. The link between flow rate and pressure difference was familiar in this experiment. Throughout the experiment, it was discovered that as the flow rate increases, the velocity increases, resulting in decrease in pressure. Based on the data they acquired, the coefficient discharge can be determined using the formula of actual volumetric flow rate, QAC, over the theoretical volumetric flow rate, QTH. According to the result of the experiment, the venturimeter provides more precise measurement than the orifice meter since its coefficient of discharge, CD, is larger. Okay, for the objective of this experiment too, the objective of this experiment is to compare the discharge coefficient of different type of flow measurement methods, to examine the relationship between the flow and pressure in flow using pilot tube, explore the corresponding flow coefficient for each flow meters, and measure the flow of meters using different flow meter, orifice plate, flow meter, and measuring nozzle, venturi nozzle, and rotameter by applying Bernoulli principle. Okay, next, for the introduction, the ability to operate flow meter, which are orifice plate, nozzle, and venturi, will be tested in this experiment for discharge coefficient comparison from each flow meter. In this experiment, we can see that when the fluid velocity increases gradually, the pressure of the fluid decreases. Flow rate measurement is critical in all industry, and there are various methods for measuring flow in pipe. Okay, next.
Many types of device using principle of Bernoulli equation has been developed to measure fluid velocity and flow rate. The type of flow meter that will be used in this experiment are orifice plate, nozzle, and venturi. The operation of each is based on the same physical principle, whereby an increase in velocity results in a decrease in pressure. First, orifice plate. First, orifice plate. An orifice plate is a restriction with an opening smaller than the pipe diameter, which is inserted in the pipe as shown in figure 1. Due to the small opening area, the fluid velocity increase, causing a corresponding decrease in pressure. The flow rate can be calculated from the measured pressure drop across the orifice plate P1 and P2. The orifice plate is the most commonly used flow sensor, but it creates a rather large non-recoverable pressure due to the turbulence around the plate, leading to high energy consumption. Refer to figure 1, the Bernoulli equation can be applied with the assumption of the flow is horizontal, steady, inviscid, incompressible between point 1 and point 2. Next is nozzle. The nozzle applies the same principle and calculation as orifice plate. The difference between nozzle and orifice plate are first the cross-section area and the shape of the retreated opening, whereby the nozzle, as shown in figure 2, is approximately a quarter ellipse. The last is venturi. The venturimeter is a device for measuring discharge in a pipe. It consists of a rapidly converging section which increase the velocity of flow and hence reduce the pressure. It then returns to the original dimension of the pipe by a gently diverges the diffuser. By measuring the pressure difference, the discharge loss coefficient can be calculated. This is a particularly accurate method of flow measurement as energy loss is very small. Okay. For the equation for the theoretical flow rate can be expressed as flowing. First equation, we can calculate the theoretical flow rate. And second equation, we can calculate the differential pressure between point 1 and point 2. The equation number 4, we can calculate the coefficient of discharge. And equation number 5, we can calculate the actual flow rate. That's all from theory for experiment 2. Next, methodology.
Next is methodology. Next slide. This is the apparatus of this experiment. Methodology part 1. First, the orifice plate were ensured to be correctly aligned and the manometer tubes H1 and H2 were fastened to the orifice plate. Second, the close control and gate valve were closed and then main switch and pump were turned on. Number 3, simultaneously, the flow control and the gate valve is slowly being opened until they reach their maximum opening level, until the water in the manometer overflow. Number 4, the ventilation valve is being opened by rotating it to anti-clockwise direction to release all the bubbles, if have, in the system. Number 5, the ventilation valve is being closed and then the gate valve is being closed. After that, the pump will open. Number 6, the ventilation valve is slowly opened until the minimum water level of 30-40 mm is reached and then the pump is being on. Number 7, the gate valve is slowly opened until the level of water in H1 reach maximum 390 mm and manometer H1 is at minimum level. All the reading, multi-tube manometer H1 and H2 and rotometer QI are recorded. All the reading, multi-tube manometer H1 and H2 and rotometer QI for 5 different values of QI were recorded by adjusting and reducing the opening of the gate valve. The minimum valve value of QI should around 200. The gate valve is being closed. Number 9, the gate valve is being closed and the pump is off. The manometer tubes H1 and H2 removed from the orifice plate. Number 10, the orifice with the nozzle was changed and step 1 to X is being repeated. Meanwhile, for the venturi, the manometer tubes are connected to H1 to H3 and similar step of I to X are applied. Lastly, after finish, all the manometer tubes from the system were removed. The flow control valve is closed and the pump also is being off. The result of this experiment is table 1 data for orifice rate. This is a data we get from the experiment for the orifice plate. Next. Table 2 data for nozzle. Table 3 data for venturi meter.
And for discussion. So the first question was, discuss the difference on water level in manometer with the different types of flow meter. Relate your answer with pressure losses associated with the types of flow meter. So from the result, we can observe that for all type of flow meter, the value of H1 is always greater than H2. So we got this from according to the Bernoulli's equation, where pressure head plus the kinetic head plus the elevation head is always constant. So as we can see, when Z1 is equals to Z2, we'll get that the pressure head plus the kinetic head equal at 0.1 is equals to the pressure head plus kinetic head at 0.2 is the same. And then according to the equation of flow rate equals to cross-sectional area times by velocity, we get that cross-sectional area at 0.2 is less than A1. So hence the velocity at 0.2 is more than velocity at 0.1. So as V2 is more than V1, pressure losses is occurred as P2 is less than P1 to balance the Bernoulli's equation. This has proven why H1 is always greater than H2, where E2 is less than A1, V2 is more than V1, P2 is less than P1, and H2 is less than H1. So for each of the flow meters, the orifice plate, the height of the H1 increases as the volumetric flow rate increases, while the height of the H2 decreases because a nozzle with an opening has a limit. The region for the opening is smaller. At H1, the height of the water level is higher because the high pressure in fluid was produced to flow through the smaller opening area. Thus, the fluid velocity increases and the pressure decreases at H2 and lessens the height of the water surface. And for the nozzle, the height of H1 increases as the volumetric flow rate increases, while the height of H2 decreases. This is because a nozzle with an opening has a limit. This opening has a restriction that causes a frictional force to occur in the tube. As the fluid increases, the nozzle acceleration, the velocity increases, thus reducing the strain, allowing a large difference in height. Thus, the decrease in pressure causes H2 reading to drop. And for venturi meter, at H1, the value of the water level is higher than H2 in the venturi meter. This happens because the venturi meter consists of a segment that converges rapidly, while the velocity is lower. It makes the pressure at H1 greater, but the pressure continues to decrease as the fluid moves through the H2, while the velocity the velocity increases, so the water level at H2 drops. So for question 2, we should discuss the difference in discharge coefficient value for each of the flow meter and ranking the flow meter according to the accuracy. So we calculated the coefficient value by taking the average, where we total up the values and divide by 5. So for the orifice plate, we got 0.356. For the nozzle, we got 0.76. And venturi meter, we got 0.90. So based on the table, we can determine the average coefficient discharge value for each type of nozzle. The most accurate flow meter is venturi meter. Average CD value of venturi meter is 0.9, which is closest to 1 compared to nozzle and orifice plate. And the average CD value of nozzle is 0.76, which is smaller than 1, which is smaller to 1, showed that the actual flow rate is so much different from the theoretical value. And the average CD value of orifice plate is 0.356, which is smaller to show to 1, that the actual flow rate is so much different from the theoretical value. So the accuracy of the flow meter is venturi meter, nozzle, and the orifice plate. And for discussion number 3, discuss the factors contributing to errors or inaccuracy in the experimental data and the possible recommendation to improve the existing results. So some of the errors are, first of all, the presence of air bubbles in the apparatus and ventilation valve was open for a short period of time, which caused the air bubbles have not enough time to escape. So which can affect the reading of the height of the manometer. Secondly is the unstable flow rate, where the height value keep changing and cause difficulty in reading. And third, what the water meniscus is formed cause the reading of the manometer is slightly hard to read. And fourth is the limitation in time response in human. So where the observer may not start and stop the stopwatch at the exact timing. And fifth is the observer eyes is not perpendicular to the scale of the rotameter and the multitube manometer, which causes parallax error. And lastly is the water leakage between the tubes and the manometer due to the lack of proper connection. And for recommendation, ensure that the air bubble is flexible and completely null to give precise reading. Next is flow rate of water must be always constant during the experiment by fully open the valve during every part of the experiment. Third is to avoid parallax error, the observer eye should be perpendicular to the reading scale. And fourth is the parallax error can be reduced by putting a white paper behind the ruler to make the water meniscus to be seen more clearly. And lastly, the reading should be taken repeatedly to get an average value and minimize the errors while taking the time reading. So next, I would present Harit for the conclusion.
Thank you, Washa. So for the conclusion, okay, next slide. Throughout the experiment, it was discovered that the Bernoulli equation can be used to observe the link between flow rate and pressure, where when the flow rate increased, the velocity increased and the pressure decreased. According to the experiment, the actual volumetric flow rate of a venturi meter was nearly identical to the actual figure, but the value of an orifice meter was slightly different. This could be attributed to the presence of mistake in the experiment process as well as the flow meter itself. It was also discovered that the coefficient of discharge of the venturi meter is higher than that of the orifice meter, indicating that the venturi meter is superior to the orifice meter. Okay. For the recommendation, we have three recommendations. First, parallel error should be avoided for more accurate result. Second, handle the stopwatch carefully so that it stops on time. Third, record multiple reading of data for better accuracy. Next, okay, this is our reference. Okay, that's all from our group. Thank you.